Hi everyone, I'm going to try to break down this chapter into a little bit more manageable bite-sized pieces. I'm going to first start off by talking about alcohols, thiols, and ethers, so naming these types of compounds, their structure, and then a little bit on their properties. I'll do a separate video on aldehydes and ketones, and then once we've kind of taken those in two small chunks, what I want to do is then talk about the types of reactions that these types of molecules undergo. So just to start off, just so we can kind of get a foreshadowing of where we're going, alcohols are going to be any organic compound that have an OH group attached to them. So I'm using that squiggly line just to represent any organic molecule, doesn't matter what, but I have my OH attached to it. So that's my alcohol. Same idea. If I have that organic molecule, but now I attach an SH, this is going to be a thiol. So very similar in structure, different in reactivity, but there's a reason for the structure looks similar. Because if you look at the periodic table, sulfur is directly below oxygen. And so if we did do their dot structures out, you would find out that both of them make two bonds. And that's what we're seeing here. There's a carbon-oxygen bond here, and I've kind of implied it there, but there's an OH bond, carbon-sulfur bond, and then an SH bond. And the last thing that we're going to talk about in this particular video is going to be ethers. So I'm going to make it a little bit more explicit. But an ether in particular is going to have this COC bond. So even though in the alcohol we had a carbon-oxygen bond and an oxygen-hydrogen, there's my carbon-oxygen bond. Oops, let me do it a little bit more clearly. There's my carbon-oxygen bond. But instead of being connected to a hydrogen like an alcohol, it's connected to another carbon. And so this is going to be an ether molecule, or an ether type bond. So let's start with naming alcohols. So again, we're going to be using the IUPAC system. And that's, again, the International Union of Pure and Applied Chemistry. It's pretty easy to name alcohols. You can write down whatever the base name is for the alkane. And so what I mean by that is, say we had CH4. The IUPAC name for that is methane, but if I drop the E and add OL, like I'm seeing here, I took one of the hydrogens off the methane, because if I look at the structure, I'm just going to do a quick sketch. Oops, it's not working. Too small. We do it on the side over here. Right, quick sketch. There's my methane. I'm going to pull one of the hydrogens off and attach an OH onto it, and now I have my methanol. A common name for this is methyl alcohol, an even older name would be wood alcohol. You might have seen that before too, or heard about that. Wood alcohol gets its name because that's from the decomposition product of wood and organic matter. If you drink this, you will go blind. We can talk about that a little bit more later when we get into aldehydes, because aldehydes can eventually turn into acids, and acids can burn out the retina in your eye. And we can apply this again to more complex structures. There's my ethane. I can pull one of the H's off, one of the terminal H's, replace it with an OH. That's what we see here. It becomes ethanol. Again, an older name is ethyl alcohol, and you might actually hear the term grain alcohol is used a lot. It's because that's the kind of alcohol that you drink. And so you can see the difference in structure is very small. One causes you to go blind. The other ones can still kill you, but it's usually used for the intoxicating effect. And it's called grain alcohol because it's distilled from grains like barley and wheat. So let's do a practice problem, right? We're going to follow a lot of the same rules that we did for naming alkanes. So what we want to do is find the longest carbon chain that has the substituent that we care about attached to. So if I do that, let me just go back to yellow for the carbon chain. So I'll go 1, 2, 3, 4, 5, I guess, right? 1, 2, 3, 4, 5, 6. Sorry, I can't count. 6. What we want to do, and we're not going to get too deep into this, but IUPAC does rank the importance of different substituent groups. We're going to treat any alkyl group as pretty much the lowest of the low. That's our least priority. Right now, our priority that's going to change the name is going to be the alcohol group. And so that's also going to dictate our numbering. So you want the smallest number of, so when we're numbering our carbons, to be on that high priority substituent group. So we see that we have a hydroxide group, or the alcohol group, on carbon 2. So if I was going to start naming this, right, we've gone through 1, 2, 3, 4, 5, 6 carbons. Oops, not do it too quickly. That's going to give me hexane. I'm removing the E, so it's no longer hexane, but I have an alcohol. So there's my hexanol. The alcohol is on the 2 carbon. And the only substituent I have left is that methyl group on the 5. So 5 methyl 2 hexanol. And again, just to reiterate, it doesn't matter which carbon I labeled as carbon 6 because they're both chemically identical. So I could call, oops, that's what one I just did. I could call that carbon 6, and I could, oops, sorry, I'm getting my buttons confused. Right, and that still would put that methyl group at the 5 position. And so again, that's just going to be a structural isomer, so it doesn't change the name. It means that the compound's the same. And we'll see that as we go through. If you can write a distinctly new name, it's a new compound. If the name is exactly the same, it just means you kind of move things in space, but it's the same molecule. And what I mean by move in space is, imagine in that last slide, like these carbons can rotate around this carbon. But don't overthink that too much. I might be saying too much. So what I have on the next subsequent slides are just a slow walkthrough. So if you want a little bit different walkthrough rather than my voice, I'm taking the exact same steps that you see here. So I'm going to leave this up to you. It's almost the same exact problem we just had, a little bit different. But why don't you give that a shot yourself, right? Applying the same steps. Step 1, figure out the longest carbon chain. 1, 2, 3, 4. Again, it doesn't matter. I'm just going up to make it quote unquote more complicated. So I can count, I have 1, 2, 3, 4, 5 carbons. So I know I'm going to be dealing with pentane. I have the alcohol is going to be my high priority substituent group. So it changes it to pentanol. That also then gives me my priority in terms of numbering. So it's 2 pentanol. And then 3, 4, 5, and I have a 4-methyl group. So 4-methyl 2 pentanol. So that's going to end our naming for alcohols. We're going to circle back towards the end to talk about a little bit more properties. I just want to get naming out of the way first. The next molecule we're going to talk about, or type of, actually we call them not molecules, we're going to call, I don't think the book mentions it, or maybe they do, maybe I went too quick. These are called functional groups because they're changing the function of the molecule. So when you attach these two, because we said alkanes are usually low reactivity, by attaching functional groups you're changing their function or changing their reactivity. So certain properties about thiols, they contain sulfur, obviously, right? But a defining characteristic is they're usually terrible smelling compounds. There was one compound that we had in the lab, it was a couple years ago when I was working at BU. It was 1,2-dithioethane or something like that, I believe. It basically reeked so bad. We opened it up in the lab and then closed it pretty much immediately and stunk up the entire floor. It was one of the few times in my life that I wanted to puke from smelling a compound, and it was one of the worst things I ever smelled in my life. So thiol groups usually have strong disagreeable odors. The reason for that is humans have evolved, and animals as well, to avoid molecules that indicate decaying organic matter. So when things go putrid or rancid, the organic compounds are basically falling apart and breaking down, and sulfur and nitrogen are being released as different compounds, and then humans have evolved to associate that with death, and basically you've evolved to avoid these compounds. Not that they inherently smell bad, it's just that you've evolved to have a adverse reaction to the smell. However, in small amounts, they can be useful because that's what gives certain funky cheeses their flavor, and onions, garlic, and oysters are also based on these thiol compounds, though usually they're in small amounts. It's also used to detect gas leaks. So anytime you smell like a gas leak in your house, hopefully you never have, but if you have, you know it smells kind of stinky. It's not because the methane, because that's actually what your natural gas is. That is odorless to humans. But what you do is you spike in a small amount of these thiol compounds, and you can definitely smell those, even in small concentrations. So how to name thiols? It's actually not much different than naming alcohols. The only difference is before when we had like methanol, it's methane thiol. Instead of having ethanol, it's ethane thiol. So you're just taking the name of the base alkane and just attaching the word thiol to it. Again, if we need to indicate the position of the thiol, so something like here when we have the 2-butane thiol, 1, 2, 3, 4, that's my main alkane chain. So there's my butane. And then I have a thiol group attached to the 2 position. So 2-butane thiol. So ethers. This will be the last type of molecule, last type of functional group that we'll discuss in this lecture. The main defining characteristic is this carbon-oxygen-carbon group. It is bent, even though when we draw it, it kind of looks like it's linear, especially down here you see with the dimethyl ether. There are 2 lone pairs on the oxygen, so it actually has the bent structure just like water does. There's more complicated ways to name ethers, but it is beyond this course, so we're going to keep it to actually the traditional way of naming ethers, mostly because the type of ethers that you would come across in terms of being a nursing student are going to be these simple ethers, and then actually some of these ethers were used as the original anesthetic. The only problem is it was easy to kill people with them, and then usually when you regain consciousness, you would vomit like crazy. So it's not a great anesthetic, but it would definitely work for, you know, if you're doing surgery or something like that, something in extreme case. So how do we name something? We're going to get to that in a second, but this is kind of like a heads up, right? Once we identify that we have an ether molecule, the name comes down to just naming what's attached to that center oxygen. So in this case, I know I have an ether, and I have 2 of those methyl groups, so therefore that's where I'm getting my dimethyl ether. So what happens if it gets a little bit more complicated than dimethyl? Well, not much more we have to do, right? Again, recognize we have our methyl group, 1, 2, 3, there's my propyl group. Remember from the last, chapter 11, YL, as we're replacing methane, becomes methyl, or methyl if you pronounce it normally. Propane becomes propyl. So the way we do that is we usually name them just in order that they appear: methyl, propyl, ether. And again, it's coming in alphabetical order, so M before P. So study check, right? Write the structures of the following. So you can pause if you'd like to do this on your own, or maybe pause after a while, but I'm going to show you how I'd go through these 3. So the first thing I notice right off the bat, I'm dealing with an alcohol with 5 carbons long. So 1, 2, 3, 4, 5. And it's at the 3 position. 1, 2, 3. That is 3 pentanol. Right, so once we get a hold of this, it actually goes quite quick. So again, ethanol. 1, 2. And it doesn't matter what side I attach the water to. So when you have small molecules like ethyl, it gets a little weird, but remember there's a carbon here and a carbon here, and then the OH is attached at the 2 position. Or actually, if we're doing by name, technically that would make this the 1 position and that's 2 position, but if you take the mirror image, they look identical. So actually you don't need to give the numbers. But that's our ethanol. And then we have diethyl ether, so 1, 2 attached to an oxygen, 1, 2. Again, getting used to these skeletal structures will help you, right? So each one of those points that I kind of filled in, that's a carbon, 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 carbon. Ethyl, ethyl is my ether in the middle. Again, right, if we're looking at ethyl, I said that sometimes it gets a little confusing when you don't have a lot of points, but maybe if you want to go through to remind yourself, just give yourself a little dark dot at each place where a carbon would be, and it makes it a little easier to follow. So those are our 3 structures. And that's exactly what we have here. So really quickly, properties of alcohol, and then we'll be done with this little brief section on alcohol, thiols, and ethers. So all I really want to pull out of this particular chapter, there's a whole bunch, and I encourage you to read it on the solubility of alcohols. Most organic compounds, I won't say most, ones that don't have very electronegative components to them, functional groups, tend to not be soluble in water, but alcohols do have OHs, which are capable of hydrogen bonding, which makes them very soluble, as long as they're small. Small molecules like ethanol, methanol, propanol are soluble in water. Then you get to butanol, and the isobutanol gets a little bit less soluble, and then you get up to things that aren't soluble, bigger than that. But what I really do care about, because this will play more relevance when we talk about reactivity, is determining if an alcohol is primary, secondary, or tertiary. The names sound intimidating, but it's not that bad, because all I'm asking is saying, all right, there's my carbon attached to that hydroxide group. The question is basically asking, how many methyl groups do I have attached? 1, it's primary. 2, it's secondary. 1, 2, 3, it's tertiary. And in all of those, I've kept the similar structure. So there's my carbon alcohol. And it's just asking, on this center carbon here that's originally attached to my alcohol, again, how many methyl, it doesn't have to be methyl, but how many carbon-containing groups are there? It just happens to be methyl here. They could be ethyl, they could be an entire molecule, it doesn't matter. But 1, 2, and 3. And so the words primary, secondary, and tertiary will also come out a couple of times for the rest of the semester. So getting used to that terminology will be helpful. So if we're going to start labeling things as primary, secondary, and tertiary, how would I go about that? Well, there's my OH group that I care about. That's my alcohol group. And then I just count up how many carbon functional groups are connected to it. I got 1 carbon functional group, and then this whole thing counts as 1 as well. So in this case, I'm going to have a secondary alcohol. Again, I'm not counting the hydrogen. So I see there's a hydrogen attached to that carbon, but that doesn't count towards primary, secondary, or tertiary. We take a look here again. Well, there's my carbon attached to the oxygen, attached to the alcohol group. There are 2 hydrogens attached to that carbon, but also this carbon chain is attached to that carbon that's attached to the oxygen. There's my primary structure. And maybe if I draw the skeletal structure, it might make a little bit more sense. Let me try this. So we have 1, 2, 3, 4, 1, 2, 3, 4, and the oxygen's on the center. So now you can see it's a lot more clearly that there are now 2 carbon things attached to that carbon that's attached to the alcohol group. If I draw this one out, we got 1, 2, 3. So 1, 2, 3. Again, we can see that there's only 1 thing attached to that carbon that's attached to the oxygen of the alcohol. So we have primary. And then we take a look down here. We have 1, 2, 3 carbon groups attached to the carbon that's attached to the alcohol. There's our tertiary alcohol. If I was going to draw that as a skeletal structure, I got 1, 2, center carbon, oxygen, 1, 1, 2. Something like that. A little bit more complicated, but we can see the center carbon's got 1, 2, 3 things attached to it, making it tertiary. And that's what we got here, secondary, primary, and tertiary. All right, so that's the end of my introduction. Those are just quick words for me to remember where to stop, but it's alcohol, thiols, and ethers.